In the previous lecture, we have started to deal with the concept of normal coordinates and normal modes. Actually, to know the concept of normal coordinates and normal modes, we have started to deal with the problem of two coupled oscillators. And the figure shown here actually represents the two coupled oscillators. You can see that a spring of a spring constant K is connected to a mass M, and its other end is connected to a wall S1. And similarly, the another spring having the same spring constant K is connected to another mass M, and its another end is connected to the another wall S2. And both of these masses are connected by a spring of a spring constant, let us say K prime. Okay, all these things you have seen in the previous lecture. Now, in this first figure, let us say this is figure A, the two masses are in equilibrium. It means the springs do not exert any force on the two masses. Now, when we displace the two masses by, let us say, x1 and x2 from their equilibrium positions and released, then you know that these two masses perform actually simple harmonic motions about their equilibrium positions. In the previous lecture, we have actually obtained the equations of motions, that is the motion equations which govern the motion of these two masses, we have obtained in the previous lecture. Okay, and we have also seen what are the solutions of that equations. Actually, our purpose for writing the equation of motion of this system and getting the solution of those equations, actually our aim was to develop the concept of normal coordinates and normal modes. So to know the idea of normal coordinates and normal modes, I am just starting with the results which we have already obtained in the previous lecture. You have seen that in the previous lecture we have obtained that the equation of motion of the two coupled oscillators are given like this. This is mx1 double dot plus kx1 plus k prime x1 minus x2 equal to 0, and the another equation of motion was mx2 double dot plus kx2 minus k prime x1 minus x2 equal to 0. Here when you say x1 double dot, what does it mean? It means this is actually the second order derivative of x1 with respect to time t. Okay, so these are the two equations of motion of this system. You can see that both of these equations contains actually the both coordinates, that is x1 and x2, which are treated here like generalized coordinates. So these are coupled differential equations of second order with constant coefficient, because this equation A also contains x2 along with x1, and similarly the equation B, which is in terms of x2, also contains x1. So A and B, which are equations of motion, are called coupled equations of motions. Actually, our aim is to now solve these equations by decoupling these equations. It means our aim is to write two equations of motions, particularly in terms of only one coordinates for each. Okay, that is called decoupling of differential equation. Now, in the previous lecture, you have seen that the solution of this equation A is given like this. This is x1 equal to a1 cos omega 1t plus phi 1 and plus a2 cos omega 2t plus phi 2. Actually here, this omega 1, which is cyclic frequency of oscillation, this is equal to actually omega naught. We have seen this thing in the previous lecture, and that is equal to a square root of k by m. And on the other hand, this second cyclic frequency omega 2 is given like this. This is a square root of omega naught square plus 2 omega c square, where omega c, you know, this is a square root of k prime over m. Okay, we have obtained these two results in the previous lecture. Now, to get the idea of normal coordinates and normal modes of vibration, let us try to uncouple these differential equations. And for this, let us first of all consider that if this amplitude term A2 is 0, then what will be the values of x1 and x2? Let us try to find. You can see, if you consider that A2 is equal to 0, then you can see these two equations, that is equation C and D. When A2 will be 0, the second term in RHS of equation C and D will vanish, that will be 0, and so this x1 will be simply equal to A1 cos omega 1 t plus phi 1, and x2 will be also A1 cos omega 1 t plus phi 1. So you can see that in this condition both of these x1 and x2 will be same. It means both the particle will oscillate actually in the same phase with same frequency omega 1 in this condition. You can see it here. When A2 is 0, x1 is equal to simply A1 cos omega 1 t plus phi 1, and x2, this is also equal to A1 cos omega 1 t plus phi 1. So you can see that when A2 is 0, then x1 is equal to x2. Okay? And x1 is equal to x2 means what? It means the two particles or the two masses oscillate together in same phase with same frequency omega 1. Okay? But if we consider that A1 is equal to 0, see these two equations. Substituting a 0 for this A1, what will be our result? When A1 is 0, you can see from equation C that x1 will be equal to A2 cos omega 2 t plus phi 2, and this x2 will be equal to minus A2 cos omega 2 t plus phi 2. You can see. So, when A1 is 0, I have written here, you can see that x1 is equal to A2 cos omega 2 t plus phi 2, and x2 is equal to minus A2 cos omega 2 t plus phi 2. Okay? So what you are seeing here, when A1 is 0, then x1 is not equal to x2 like the first case, but x1 is equal to minus x2, you can see. But the frequency for both of these oscillations are same, and that is equal to omega 2. Okay? This minus sign actually implies that in this condition the two masses oscillate opposite to each other. And when you say that the two masses oscillate opposite to each other, what does it mean? It means both are oscillating in anti-phase. There is a phase difference of pi or 180 degree of the oscillation of the two masses. Or in other words, you can say that they are out of phase by pi radians. Okay? So we have obtained the two results. When A2 is 0, then x1 and x2 both are equal, and both particles or both masses oscillate in same phase, in same direction, and with same frequency omega 1. But when A1 is 0, then x1 you can see is equal to minus x2. So in this case, the frequency of oscillation of two masses are same, that is equal to omega 2, but they vibrate in opposite phase. So actually there are two modes of vibration here, you can see, and these two different modes of vibration are actually called normal modes of vibration. So I have mentioned it here. You can see that two such modes of oscillation involving a single frequency are called normal modes of vibration. Okay? Now to get the idea of normal coordinates, let us do some of the algebra. You can see we have actually obtained two equations of motion in the previous lecture, which I have mentioned it here in equation A and in equation B. So to get the concept of normal coordinates, let us add these two equations. That is, we are going to add equations A and equation B. See these two equations. When you will add these two equations, as this term k dash times x1 minus x2 in equation A is positive and in equation B it is negative. So when we will add these two equations, these two terms will cancel out. Okay? These two terms will cancel out. And the remaining two terms will get added. So what will be our result? When you will add mx1 double dot and mx2 double dot, m will be a common factor and there will be x1 double dot plus x2 double dot. And in the second term, k will be a common factor and there will be k times x1 plus x2. So after adding equations A and B, what will be our result? You can see here. When we will add A and B, our result will be what? Just the page will be okay, don't worry. See here. So when we add these two equations, our result is m times x1 double dot plus x2 double dot plus k x1 plus x2 equal to 0. Now you know that this x1 double dot means second order time derivative. Okay, so this term can be written as m times d2 by dt square x1 plus x2 and plus k x1 plus x2 and equal to 0. Okay. Now take this m as a common factor, or you can say that we will divide this equation both sides by m. So in first term m will cancel out and the second term will be k by m times x1 plus x2. Okay. Now this k by m, you know this is actually equal to omega naught square, or omega naught is equal to a square root of k by m. So this result can be written as d2 by dt square x1 plus x2 plus omega naught square x1 plus x2, and that is equal to 0. Okay. Now we will subtract this equation B from equation A. We are going to subtract equation B from equation A. See here. When you will subtract this equation B from A, then this minus k prime x1 minus x2 will become plus. So these two terms will get added and this will be 2k dashed x1 minus x2. Okay. And here there will be k times x1 minus x2. So x1 minus x2 can be taken as a common factor, and and the remaining term will be k plus 2k prime, 2k dashed. Okay, 2k dashed. So after subtracting equation B from A, what will be our result? You can see this will be m times x1 double dot minus x2 double dot plus k plus 2k prime times x1 minus x2 equal to 0. Okay, and this can be written as d2 by dt square x1 minus x2, as m has been taken as a common factor. So in second term we will divide by m to both terms. So this will be k by m plus 2k prime by m times x1 minus x2 equal to 0. Okay. Now this k by m, you know this is equal to omega naught square, and k prime by m, you know this is omega c square. You have seen this thing in your previous lecture. Okay. So this factor is written like this. This is omega naught square plus 2 omega c square. Okay. So our result is now d2 dt square x1 minus x2 plus omega naught square plus 2 omega c square times x1 minus x2 equal to 0. Okay. Now to simplify these two equations which we have obtained in equation 3 and 4 after adding and subtracting the equations of motion, we introduce actually two new coordinates. Let us define those two new coordinates like this. We consider that this capital X1 is our first new coordinate, and this is defined like this. This is x1 plus x2 divided by 2. We define like this. And the another new coordinate we introduce is capital X2, and we define this capital X2 like x1 minus x2 divided by 2. Okay. So from here you can easily see that x1 plus x2 in this condition will be equal to 2 capital X1, and x1 minus x2, this will be 2 capital X2. Okay. So in equation 3 and in equation 4, here at the place of this x1 plus x2, we will write 2x1. Here also we will write 2x1. So 2 will be a common factor, and that will removed because in RHS there is 0. So instead of x1 plus x2 in this equation 3, we can write x1. Okay. And similarly, in this equation number 4, you can see instead of this x1 minus x2, we will write 2x2, and here also we will write 2x2. Again, this 2 will be a common factor, and since in RHS there is 0, so that 2 will be removed. And instead of x1 minus x2, we can put capital X2, and here also capital X2. Okay. So what are our equation 3 and 4 now? You can easily see. Our equation 3 becomes d2x1 by dt square plus omega 1 square x1 equal to 0. Actually, this omega 1, you have learnt in the previous lecture, this is equal to omega naught, and this is equal to a square root of k over m. Okay. And the fourth equation, you can see this is actually equal to what? Our fourth equation is this much, and this will be what? This will be d2x2 dt square plus omega 2 square x2 equal to 0, where omega 2 is equal to a square root of omega naught square plus 2 omega c square. Now see the form of these two equations. If I will ask you that see the equation, first equation in this equation 6, and tell me that is it a equation of SHM or not? Your answer will be definitely yes. This is equation of SHM. When I will ask you that if it is equation of SHM, what is the displacement or what is the coordinate of the particle? You will say that this capital X1 is the coordinate or displacement. And when I will ask you what is the frequency of this simple harmonic motion, your answer will be omega 1. Okay. Now in this equation there is only one coordinate, that is capital X1. So this is an uncoupled equation of motion. You have seen that previously when we have written the equation of motion, in each equation both the variables x1 and x2 were present. So those equations were called coupled differential equations. But now you can see that those two coupled differential equations have been uncoupled, because in this first equation the only variable is x1, and in this second equation of motion the only variable is x2. So these are the two uncoupled differential equation of second order, which are actually the equation of simple harmonic motion with frequencies omega 1 and omega 2. Okay, omega 1 and omega 2. So you can say that the motion of the coupled system is now described by two uncoupled differential equations which I have defined in this equation 6, and each of which describes the simple harmonic motion of single frequency, either omega 1 or omega 2, and in terms of the single coordinates which are x1 or x2. Okay. Now, what will be the solution of these equations defined in equation 6? This is the well-known differential equation which represents simple harmonic motion, and we have studied several times the solution of simple harmonic motion. You know that the solution of equation of motion of SHM is written in several forms. It is either in terms of cosine function, or in terms of sine function, or in terms of e to the power plus minus I omega t. Okay. So here I am writing the solution of these two equations defined in equation 6 in terms of the cosine function. You can write that the solution of this equation first in equation 6 is x1 equal to a1 cos omega 1 t plus phi 1, and the solution of this second equation you can write this is x2 equal to a2 cos omega 2 t plus phi 2. Here actually a1 and a2, you know, these are the amplitude of the oscillations, and omega 1 omega 2 are frequencies with which this motion takes place, and phi 1 and phi 2 are actually phase constant or initial phase, that is phase of the oscillation at t equal to 0. Okay. So there are two independent motions. Here you can see that these two simple harmonic motions obtained after decoupling of coupling of the coupled equations are called normal modes. These two simple harmonic motions, these are called normal modes. And you can see that each mode of vibration has its normal frequency either omega 1 or omega 2. Okay? And these motions are described in terms of the coordinates x1 and x2, that is capital X1 and capital X2. And these capital X1 and capital X2 are actually called normal coordinates. These are called normal coordinates. Okay? Normal coordinates. Okay. So I think you have understand how the idea of normal coordinates and normal modes of vibration is developed. Actually, first of all, we have obtained the coupled equations of motions. Then, by simple technique, we have uncoupled those differential equations, and the uncoupled equations are obtained by introducing the concept of normal coordinates. When we define the capital X1 and capital X2, which are called normal coordinates, then you have seen that actually the equations of motion become uncoupled, and then those coordinates which actually uncoupled the coupled differential equations are called normal coordinates. Okay. Now, in fact, the normal modes of vibration may be of two types. And these two types of normal modes of vibration are called symmetric mode and asymmetric mode. Okay, symmetric mode and asymmetric mode. So let us first of all see what is the symmetric mode of vibration. In fact, when, as you have seen that there are two modes of vibration in this case, but when we consider that any one mode of vibration is absent, if you consider that any one mode of vibration is absent, then there will be only one mode of vibration, and that only one mode of vibration will describe the motion. Okay? So, in that condition, we can take either x1 equal to 0 or x2 equal to 0. Okay? Because you have seen there are two equations of motions, this much and this much defined in equation 6. And the equation 7 represents their solution, and equation 7a represents one of the mode of vibration, and equation 7b represents the another mode of vibration. So as I have told you that when we consider that only one mode of vibration is present and another is absent, in that condition we have to take either x2 equal to 0 or x1 equal to 0. So let us first of all take what happens when we consider that x2 is equal to 0. Okay? When x2 is equal to 0. When x2 will be 0, then the motion will be completely determined by the coordinate capital X1. This capital X1 will be responsible for the motion of the particle, and we can describe the motion in terms of this capital X1. Okay? Now let us see, when x2 is 0, then what will be this capital X1? We try to find it. As you know that we have defined this capital X2 as x1 minus x2 divided by 2. Okay? Can you remember? We have defined it. But here we have considered that x2 is 0. So you can write 0 equal to x1 minus x2 divided by 2. Okay? 0 equal to x1 minus x2 divided by 2. And so this x1 minus x2 is equal to 0, which means x1 is equal to x2. Okay? So in this condition, x1 and x2 both are equal. It means the displacement of the two masses will be equal in same direction. Okay? Now, what will be the value of x1, capital X1 in this case? You can see. As you have defined this capital X1 like this, this is a small x1 plus a small x2 divided by 2. Okay? But as we have seen, when x2 is 0, then this capital X1 is equal to capital X2. So instead of this capital, in this condition, a small x1 is equal to a small x2. So in this condition, when we will write x1 instead of this x2, our result will be 2x1 by 2. But if we replace this x1 by x2, then our result will be 2x2 divided by 2. Okay? So now this 2 and this 2 will cancel out, and you can see that this capital X1 in this case is equal to a small x1, and that is equal to a small x2. And you know that this x1 is equal to a1 cos omega 1t plus phi 1. Okay? So this is the first mode of vibration, and in this condition you can see the displacement of both of the particles. That this x1 is displacement of the first particle from equilibrium position, x2 is the displacement of second particle or second mass from the equilibrium position, but both are equal. Both are equal. And both masses vibrate with same frequency omega 1 and in same phase. Okay? In fact, when the two masses have equal displacement, equal frequency and equal phases, then such a mode of vibration is called symmetric mode of vibration. Okay? What is symmetric mode of vibration? It means when the both masses have equal displacement, equal frequency and equal phases, then we say that the particles are vibrating in symmetric mode, or the mode of vibration is symmetric. You can see this in this figure. I have shown here that this is mass m, which has a displacement x1 in rightward direction. Then this another mass, this is first mass, this is second mass. This second mass has also displacement x2 in the same direction, that is in the direction of x1. And at the same time, x1 and x2 both have also equal magnitude. Okay? Or it is also possible that if the displacement x1 is in leftward direction, then x2 will be also in leftward direction. Okay? Also in a leftward direction. So this figure represents the symmetric mode of vibration. But what is anti-symmetric mode of vibration? For this, let us now consider that x1 is equal to 0, capital X1 is 0. So when x1 will be 0, then the another coordinate x2 will describe the motion of the particle. And what will be the value of this capital X2 in that condition, we will now see it. As you know that this capital X1, this is the first normal coordinate, which we have defined like this is x1 plus x2 divided by 2. But we have assumed that capital X1 is equal to 0. So it means this small x1 plus small x2 is equal to 0. And therefore, you can say that x1 is equal to minus x2. x1 equal to minus x2. Mark this. In this case, x1 is equal to minus x2. Now, you know that this capital X2 has been defined like this, x1 minus x2 divided by 2. So when we will replace this minus x2 by x1, then there will be x1 plus x1, that is 2x1 divided by 2, and this 2 and 2 will cancel out. But if we replace this x1 by minus x2, then this will be minus x2 and minus x2, that will be minus 2x2. So this can also be equal to minus 2x2 by 2, and here this 2 and 2 will also cancel out. So what you are seeing here, this capital X2 is equal to either a small x1 or minus x2. So you can say that capital X2 is equal to a small x1 and it is equal to minus x2. But you know that x2, capital X2 is equal to this much. You have seen earlier, capital X2, when you have written the solution of uncoupled differential equation, you can see here this x2 is equal to this much. Okay. So in this mode of vibration, both the masses vibrate in opposite direction, because x1 is not equal to x2, but it is equal to minus x2. It means both are vibrating in opposite phases, but with same frequency, and the frequency with which the two masses are vibrating, that is equal to omega 2, and that omega 2 is equal to a square root of omega naught square plus 2 omega c square. Okay. So in this mode of vibration, you can see that the two masses have equal but opposite displacement. Okay. But the frequency of oscillation are same, that is equal, and the phases are opposite. And such a mode of vibration is called antisymmetric mode. Such a mode of vibration is called antisymmetric mode. And I have shown this fact in this figure. You can see here that when the first mass suffers displacement in rightward direction, you can see the second mass suffers the equal displacement. Equal means equal in magnitude in leftward direction. Okay. So x1 and x2 both are in opposite direction. Or when you can say that the first mass suffers displacement in leftward direction, then this second mass suffers displacement in rightward direction. Okay. So this is antisymmetric mode. So I hope after these two lectures on the coupled oscillators and normal modes and normal vibration, the concept of normal coordinates and normal modes definitely have been clear to you, I hope. So watch the video seriously, and if you have any problem, you can write your doubt in the comment box. I will try to solve solve your problem. Okay. Thank you very much.